Now that you have the ability to integrate, which we know is also another word for antidifferentiate, which we're not going to use anymore because it's like way too many syllables. Integrate is easier to say, so I'm saying integrate. Having an ability to integrate and apply given initial conditions to find particular solutions is essential to your success in this class. So it's going to be on the AP exam what we're going to do today for sure. It's always there in multiple places every single year, so you need to know it. This thing, particular solutions. Yesterday we called the solutions we were coming up with, the integrals with that plus c, we called those general solutions. Today we're going to learn how to find particular solutions. And all it means is they give us some sort of condition. It could be an initial condition, or it could be some sort of situation that happens somewhere along the way. Some sort of value that they give us that we're going to substitute into the general solution and then solve for c to find out what c is, to get our particular solution. So that's basically all we're doing. In fact, you already knew how to do that. And it would have made classes like physics much easier if you knew how to do it, especially when you're talking about projectile motion, which we're going to get into. We're finally to the part where we get to puke off cliffs onto people's faces. The particular solution to a problem is one in which you use a given piece of information. Could be an initial condition, doesn't have to be an initial condition. You need to recognize when it is and when it's not to determine the value of c, the constant of integration. Okay? That's what we're doing today. So for example, find the general solution of y equals the integral of 3x squared plus 1 dx. And then we're going to let c equals negative 2, negative 1, 0, 1, and 2, and graph all of those resulting equations on our calculator. And we'll take a look at what's happening. So, and then we'll answer this question right here. First we need to integrate. So let's get that integral down. We get y equals what? Okay, and can I not write that down? Do I have to write that down? Okay, so let's go ahead and integrate it. X cubed, because the derivative of x cubed is 3x squared. What else? Plus x, because the derivative of x is 1, and then the plus c that we have to include, the constant of integration, because there could be a number there that we took the derivative of and it disappeared. Right? Okay. So now we're going to let c equal negative 2, negative 1, 0, 1, and 2, and that's going to give us a whole bunch of equations. So I have y equals x to the third plus x minus 2, y equals x to the third plus x minus 1, y equals x to the third plus x plus 0, y equals x to the third plus x plus 1, y equals x to the third plus x plus 2. What's happening each time to the graph? Yeah. So on our calculators, let's go ahead and graph that. It's kind of where I was going with that. But I didn't feel like graphing it on my calculator, so I went ahead and graphed it on Sketchpad and then put it on here so that we could see it. But the point is, your graph should look like this, right? Okay. And maybe your window settings are a little bit different so you can see more of this graph. A few questions about the behavior of these graphs. You can see what happens here. We're kind of, doing the same thing each time here. But in this region here, as these lines extend farther down, or in this region here, as these extend farther out, will they cross? Give me some vocabulary for what's happening from here to here to here to here to here. What are we doing? Better vocabulary than shifting. Vertical offset means a what type of transformation? It's a translation, yeah. Right. We'll say it louder so I can hear you. This is a translation. We're translating up and down, okay? Is the function itself, is the graph of the function itself changing in any way aside from its location? No. So therefore, if I have shifted this thing down 1 here, then I have shifted it down 1 here as well, and I've shifted it down 1 here as well. So if you think about it that way, as this extends out farther and farther, are these going to cross? No, they will never cross. They might appear to become 1 as we get farther and farther out, and that's just the nature of the scale of our graph when we graph it, but they won't cross, okay? This is called a family of graphs. The function itself gives me this guy right here with no c value. But once I include a c value, c is 1, c is 2, c is -1, c is -2, then I start getting these translated graphs. What is c? Yes. What is it? Yeah, it's just the y-intercept. We plugged in 2, 1, 0, -1, and -2 for c. If I back it up, c was those numbers. So in the particular solution, what is c? It's the y-intercept. All right, so that last example, we just plugged in values of c to see what happens to the graph. And now we know that c is the y-intercept. And the y-intercept, when we're talking about real-world situations, is whatever the initial value is. When time is 0, the height is what? Something like that, okay? So keep that in mind, because we're going to start using it now on problems like this. Find the general solution of capital F prime of x equals 1 over x squared, as long as x is greater than 0. And then find the particular solution that satisfies the initial condition, f at 1 equals 0. Technically, this is not an initial condition. It satisfies the condition f at 1 equals 0. Why is that not an initial condition? Because f is at 1. Yeah, if f was at 0, that would be an initial condition. Okay, notice the notation here. We didn't write little f prime of x. We wrote big F prime of x. Does that have any significance at all? If I give you an original function and I call it f of x and I take the derivative, I get f prime of x, right? If I take f prime of x and I integrate it, don't I just get f of x back? Yeah. So is there any significance at this point to that capital F? Not really. It's just notation. Okay? All right. So we want to integrate that. What should I do first? How should I rewrite it? So f prime, capital F prime of x equals x to the -2. What am I going to do? Add 1, just plus 1. If I rewrite capital F prime of x as like a dy over dx, then I need to write the differential form, so I wind up with a dx over here. If I integrate both sides, I wind up with capital F of x equals, I need a dx there. What is this? You're not wrong so far. We added 1 to the exponent, so we have to over -1 divide by the new exponent plus c. Okay, so I can simplify that. F of x equals the negative from this guy and then 1 over x plus c. That's the general solution. It doesn't say find the general solution. If it did, then that would be it. We want the particular solution. So what do I do? No, we don't. This is not the initial, it's not technically an initial condition because that's not f at 0.
Well, it's in f at 1 when you plug in 1.
There you go. F at 1 equals -1 over 1 plus c. No. Yes. F at 1 is 0. So I'm going to say equals 0. Okay? F at 1 is this. F at 1 equals 0. So F at 1 equals 0. And now solve for C. So this is negative 1 plus C equals 0. Add 1 to both sides, C equals 1. So now I can write the general solution as a particular solution. F of x equals negative 1 over x plus 1. So be careful. Don't just assume that the initial thing that you're given here, or this condition that you're given, is actually the initial condition. It's not necessarily the y-intercept. It's only the y-intercept if f at 0 is what you're given. Okay? So that's kind of tricky. You do need to substitute in. All right, time for some physics. What is the acceleration due to gravity in a standard coordinate system? And let's just go ahead and use metric. (9.81 meters per second squared. So acceleration equals 9.81 meters per second squared. Huh? Yeah. Let's talk about acceleration due to gravity in imperial units. Like miles, feet, yards, inches. Nobody remembers that one? You guys work in metric mostly? Yeah? How much do you weigh in kilograms? Oh. I guess you don't. 32 feet per second squared is the acceleration due to gravity in imperial units. A nicer number, yeah. But typically we work with metric in physics. So think back to when we worked with position, velocity, and acceleration. Think back. How were they related? Okay, so the notation we used for position was s of t. Okay, and then velocity was s prime of t. Acceleration was the derivative of the velocity, which means that that must be s double prime of t, right? So if I have the acceleration, which is sitting right here as a function, a of t equals 9.81, what is the velocity function? V of t equals 9.81 t plus c. What is c? What is it though? Really? Initial what? Initial velocity, which in physics, you physics people, we called v naught. That's right. So that c turns into v naught. What did you hear it called? Yeah. That's fine. It's called v sub 0, v naught. Not NOT. So if I integrate again, I'll get my position function. S of t equals, a little bit tougher, yeah, we're trying to integrate to get our position function. What do you got? So 4.9 t squared plus yes, plus c. Okay, what is that c? Initial position, that's right. And we call that S naught, that's right. Not snot. So the result is for free fall problems, projectile motion problems, strictly in the y direction, you have an acceleration function, a of t equals 9.8. We can use 9.8, that's fine. We have a velocity function, v of t equals 9.8 t plus the initial velocity, which if you're holding a coin or something just here and you let it go, the initial velocity would be 0. We have the position function, s of t equals 4.9 t squared plus v naught t plus s naught. These three equations right here, when you took physics, were what you were using constantly, over and over. And all three of them can be used as a system of equations to find any sort of variable that you don't know. Yeah, for sure. Initial position. S represents position, V represents velocity. The subscript 0 in physics represents initial something. If you were to look back in your physics book, is anybody in here in physics right now? If you look in your physics book, in the free fall problems or projectile motion problems, you will see equations that look exactly like this. Every single time, the 4.9 or the 9.8 is there, depending on what you're looking at. And every single time, the given value for the initial height is sitting right here. The given value for the initial velocity is sitting right here. If you have no initial velocity, this term disappears. Okay? It's always there. All right, you drop a ball from a height of 50 meters. That's all the information I have to give you now. That's it. Now I got to ask the question. Write an equation for the position of the ball as a function of time. We can do that. When does the ball hit the ground? So just to drive home what it is that we're doing here, we're given one thing, and it's in what kind of units? Meters. So that's going to be metric system, okay? So that means that our acceleration is going to be what? 9.8. Technically, you're right, 9.81. But we're going to make life a little bit easier. Write an equation for the position of the ball as a function of time. I have acceleration right now, so I need to integrate once to get velocity. And my velocity equation is going to be t plus v naught, which is 0. So I could write the v naught, or I could write it as a c. But once I plug in that initial condition that is not actually given to me, except for in words, you drop a ball. If I'm dropping a ball, then I'm holding it out and I'm letting it go. And its initial velocity then is 0. So this right here goes to 0. My velocity equation then is just v of t equals 9.8 t. But I want the position equation, so I need to integrate one more time. S of t equals what? Plus, normally there would be a v naught t, but v naught was 0, so that term never shows up. Plus s naught. And that's the initial position, which was given to me. It's 50 meters. So this s naught becomes 50. So I have s of t equals 4.9 t squared plus the 50. It says write an equation for the position of the ball as a function of time. I did. When does the ball hit the ground? It will hit the ground when position is 0. So that means I need to set the equation equal to 0. This becomes 0. That's position right there. So I have 4.9 t squared plus 50 equals 0. So I move the 50 over, I divide by 4.9, I get t squared equals what? I subtract the 50 from both sides, which gives me, I divide both sides by 4.9, which gives me, and then I do what? Square root but what? Yeah. So that's not the case. That's not what's going to happen. We have to back up because you guys let me go all the way through that thing without reminding me that acceleration due to gravity in a standard coordinate system is negative. That needs to be negative. That needs to be negative. Which means that's negative, and 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 that's negative. That's all right, I forgot to. Why is it negative? It's a directional, yeah, it's a vector. So we have y and x. Positive y is up, negative y is down. Gravity pulls down, so that's why we have to say negative here. Okay, I apologize for that. I shouldn't have done that. Went way too far. So this is actually negative here. That's negative. That's negative. That's negative. That's negative. That's negative. And now when I subtract the 50 from both sides, everything's fine. But now when I divide both sides by that negative 4.9, it turns positive. What's 50 divided by 4.9? Like 10-ish? 10.1 maybe? I have no idea. We're using a calculator, so it doesn't really matter what order you do it. 10.2? Okay, and then you square root both sides. So t equals plus or minus 3 point, give me 2 decimal places. 19. And obviously we can't have a negative time, so we discard that negative sign. T equals 3.19 seconds would be your answer. Slightly different problem this time. You throw a ball upward this time with an initial velocity of 64 feet per second from on top of an 80-foot cliff. Find the position function as a function of time. When does the ball hit the ground? So there's a lot more going on in this problem. But still, the only information I have to give you is right there. That's all the given information. What should we do? Yes, we are using feet, not meters. So we're going to want the feet per second squared acceleration. So A equals negative 32 feet per second squared. Now what? Velocity equation would be, let me write A of t, and then V of t would be? Why 64? But why not negative 64? We'll go through it upward. So here's our coordinate system. We threw that thing up, which means it has an initial velocity that's positive. So I'm going to write plus 64. Okay. Then S of t equals the plus 80 comes from the fact that we threw it off or up on a 80-foot cliff. So there's your equation. All right, we want to find the position function as a function of time. That's it right there. When does the ball hit the ground? When your position is 0. So what do I do? Set it equal to 0. Oh, you want to factor it? Yeah, so if you think about this, we threw the ball up, and now it's coming back down. All the way down to the ground. Okay? Or we threw it up like this, and now it's going to come down all the way down to the ground. Or you threw it straight up in the air, but the wind pushed it just enough so that it edged over the cliff, and it's going to come all the way down to the ground. Either way, it's coming all the way down to the ground. Okay. So we want to put 0 in here. No, that's a great question. We want to put 0 in here. And once I put 0 in here, I don't like that negative squared term, So I'm going to move everything over to this side and have the 0 over there. So that gives me 16t squared minus 64t minus 80 equals 0. Is everybody okay with that? Okay, now what? Does 16 go into 64 and 80? $16 how many times into 64? Or 64 how many times? 4? 4 times 6 is 24. Yep, that works. How many times does 16 go into 80? 5. So I could divide everything by 16 right now. And that gives me t squared minus 4t minus 5 equals 0. Now what?
Now we can factor it.
If it factors, you can factor it. If we didn't have a GCF up here, we would kind of be stuck and we wouldn't be able to factor it very well. Does this factor? In order for it to factor, what has to happen? Two numbers. Come on, Algebra 1. Two numbers that multiply to give me negative 5 and add to give me negative 4. Are there two numbers that do that?
Yeah.
Probably. Negative 5 and positive 1. So we have t minus 5, t plus 1 equals 0. Now what do we do? Zero product property. Solve for t. T minus 5 equals 0, which means t equals positive 5. T plus 1 equals 0, so that means t equals negative 1. Can't have negative time, so it has to be t equals 5 seconds is your answer. Okay? What if it didn't factor? Quadratic formula. Do we remember the quadratic formula? X equals negative b. It's a good thing I'm listening to everybody. This is most likely where you're going to go most of the time on these problems. So get the quadratic formula back in your random access memory. Okay, another question here that can be asked, and it frequently is asked. What is the ball's maximum height relative to the ground? I could also ask, what is its velocity when it hits the ground? Find the maximum of the equation. That's right. When the ball's maximum height is reached, we will be here, right? So how do I find the maximum height? Take the derivative, which we already have. It's the velocity equation, and do what with it? Because at its maximum height, its vertical velocity will be 0. And then it will start to fall back towards the earth. Perfect. So we take this equation right here and set it equal to 0. Negative 32t plus 64 equals 0. Basically, you're finding a critical number. I'm going to move this 32 over here. 64 equals 32t. Okay, divide by 32 and we get 2 equals t. 2 what? 2 seconds into this ball's flight, it reaches its maximum height. Now you plug it back into the position function to find out what that height was. So s of 2 equals negative 16 times 2 squared plus 64 times 2 plus 80. And then you enter all that into your calculator. Well, 16 times 4 is negative, so that'll be negative 84. That's 128 there. 144 feet. So we have it hits the ground at time equals 5 seconds. We have it reaches its maximum height of 144 feet at 2 seconds. What is the velocity of this thing when it hits the ground? When it hits.
Well, we have to plug 5 seconds.
Plug 5 when it hits into the velocity. So V, this wasn't asked, but it will be. So V of 5 equals negative 32t plus 64. Sorry, negative 32 times 5. Negative 96 feet per second. And what is the significance of that negative sign? It's going down. Okay, so you can leave that negative sign there, or you could say negative 96, or you could say negative, sorry, you could say negative, wow. You could say 96 feet per second down. Or you could just leave it, because obviously my brain is not even letting me say 96 feet per second down. So just leave it as negative 96 feet per second. Good? Okay.